Does anyone want to comment about recent papers?
There was Aiden and Michael's paper on the archive this morning, I think, on the large N limit.
Yeah, that was a great paper.
Yeah.
That's a comment.
I have a question. So there are these people who do field theory, and I mean that's where they were this tensor model first arose. It's only those models also have other vacuum, probably like an integral version of what you consider.
But what field theory?
He just means tensor models.
Tensor model. Yeah, tensor model. Yeah, sorry. So if the people were, well, in the past, Grau and other collaborators consider the matrix integral version, but so an integral version of the.
Yeah.
By integral, I mean just an integral where the integration variable is a tensor with, let's say, 3 indices. And maybe just was that quadratic. I don't remember what action they had.
So,
Exactly that.
no, generically, this is gonna be an issue. There are some papers like Igor has he calls it the prismatic model where, I guess it depends. So first of all, there's a bit of an issue with the sign, like we were able to come up with an extensively positive state, but not an extensively negative state. For at least for some of these models. And so right off the bat, that means if you're free to choose the sign in front of the potential, then it's unclear if this is even an issue. And I do mean unclear. To me, it's not clear either way. But
Are you discussing models of bosons? Because
yeah,
Okay.
Yeah, I think that's what they had. So I think they had bosons, so I don't remember where they had the quadratic and the cube
No.
quartic term.
The typical thing was they had a quartic action.
Just the quartic, yeah.
But their models were even more sick than ours in a sense, because they had unbounded potential from below. Like the P spherical constraint is crucial for making our model well defined.
well, no, well, that is true, but they also, like the prismatic model, for instance.
Yeah, that's true.
Is a positive definite potential. And so does not have any known issues related to the stuff we raised.
Can you remind us what potential it is?
God, can I? It's, you have a bunch of 3 tensors and they contract in a way that makes a triangular prism.
I see.
So I could probably draw it on the board.
Reflection positive.
Why didn't you draw it on the board?
Okay, geez. Okay, so first of all, let's hope I'm getting it right, but, so, a bunch of, it's a sextic or whatever you call it, action. And the indices contract like this. So notably, if you view this guy as one tensor, it's the square of this tensor, so it's positive definite. And this guy, right, would be some different 3-index tensor. And it's the square of that. So, it's positive definite.
There are 3-index tensors and 4-index tensors?
No, it's only 3-index tensors. I'm just bad at drawing. This is not an intersection. This is something,
Okay, good.
It goes
So each
through.
vertex is a tensor or
each vertex is a tensor. Maybe a better way to draw it would be like
yeah.
a superhero logo. Like this. There you go. It's planar now.
And is this model shown to have melonic graphs?
I believe so. I don't actually remember that part, but I think it does, yes. And it's positive definite, so the specific issue we raise isn't gonna blow it up. I am completely open to the idea that some issue still blows it up. But I don't know what the issue would be.
So in your model, the potential was it, I guess it was negative, but was it the negative definite or it had a?
No, it was not,
No sign.
yeah. It actually depends on which exact model we go with. I think we ended up going with a 1 tensor contracted with itself in a certain way, and there it depends on the sign in front. If it's 4 different tensors contracted with itself, then obviously it doesn't depend on the sign up.
Right.
But here, yeah, you can pick the sign that has positive definite and then,
But for your story, you had one tensor, right?
Yeah,
So in that
yeah, we
one
ended up
tensor,
with-
You could have either any sign or,
if it's one tensor, then for our story, you need the sign to be such that, one specific state where all the fields are one
Right.
is very negative. So,
let's say you choose that sign, then.
yeah, if you choose that sign,
Can it be
then,
positive also, or?
Well, if it's positive, it's healthy, is the statement, or at least that our argument that it's unhealthy doesn't apply.
we could not find a way to get for the sign we chose, we could not find a way to get super extensively positive potentials, if that's what you're asking.
Yeah. Right, maybe I'll just summarize the state, like the statement is, we have a sign, the sign doesn't matter in perturbation theory. The sign does matter for constructing a super extensively negative state. We chose the sign that gives you a super extensively negative state. But if you flip the sign, the state that we pick is not super extensively negative, so the model is probably healthy. We're not sure, but at least we can't prove that it's unhealthy.
I guess I was asking a more trivial question, so you have some function. The potential, does that function have a definite sign or it has both signs?
It has both signs. If you change your function, the sign will change. But it's not symmetric.
You can get a negative output or a positive output.
Yeah, that's what that is. Yeah. But it's not symmetric.
Okay. it's
Yeah.
not symmetric,
Yeah. I guess as one of the authors on this paper, I feel okay shifting the topic away from it. Another paper that I saw that came out, I think last night or the night before, was this BPS decoupling limit paper, where they were saying that they had this like very nice story for studying all the decoupling limits that generate holography. And I didn't really understand their story. It wasn't clear to me how their story went beyond Juan's original paper and the original BFSS papers, but they were claiming that they had this like unified picture that ties them all together. The thing that I was more interested in than that, since that seemed like more of a framework thing than a new physics thing, was they were claiming that they could derive new TT bar like deformations. They could like have this procedure for deriving TT bar deformations in general holographic models, which I was interested in the context of BFSS. But I cannot answer any questions on this paper because I do not understand it. I'm just saying what was in the abstract and my understanding of the introduction.
What like a little strength type thing?
What?
You mean, basically the holography, the different proposals that, one proposal that sounds more like what you're describing would be the little string, TT bar connection.
I think they also say it in the context of little string, but I was thinking just in the context of like, what is the TT bar deformation for BFSS and BFSS like models? Like if I give you a generic holographic model, what is the TT bar deformation that pushes you into the bulk? That was the question that I was interested in, which I thought they were claiming to answer. But I might have misinterpreted it.
Another way of thinking about TT bar where it turns more like into a number goto or bonito type.
Yeah.
But that's a single trace deformation.
Yes.
Sorry.
So if you look at the spectrum of an individual string, then the number goto deformation is the TT bar. Now, I'm not sure if this makes sense, but number goto and bonito have sort of a similar flavor, so there might be some related between bonito. The theory looks surprising that you can get it already sort of from a top down. Except for a little string. I didn't look at the picture.
I feel it's slightly misleading to call this one. I mean,
Correct.
conflate those two. That's more like a single trace deformation. Yeah, it's an irrelevant deformation. Divisional background.
This might also be what they meant though. Again, I was just quoting what they said, so they might be referring, when they say TT bar, they might be referring to what Herman is saying, and saying that's a little bit misleading, so that might be, but that might be what they're saying.
This is a bit minor, but about the bar, okay, there's one direction we're doing, but one direction kind of. Linear telecom for the single trace version. So in what sense is that like, I thought that's like kind of not a decoupling, but that decoupling will give us ADS. So it's, what does it mean to be decoupling?
Well, I don't know what this recent paper really did, but I think TT bar and this other deformation we're now talking about should be viewed as logically distinct.
Yeah.
So this other deformation is typically a deformation as they go to the UV, it takes us away from the decoupling limit. So for example, for n equal to 4 super mills, it would be like adding some operator trace f to the 4. And well, if you start from ADS, it makes the sphere size grow, right? Preserves all 16 supercharges. And so if you have the brane coupled to flat space, right? You have that operator turned on. So you can say that I mean, it would be, yeah, you can say that deformation is the one that takes it to flat space, though this language would be, right? It's more precise to say that if you start from flat space and you go down to ADS, you have this irrelevant deformation. And the same is true, well, when you have something like the D1, D5 system, well, there are different deformations, but one of them is the one that would take you to this linear dilaton background, so the near horizon limit of 5 rings.
Yeah, the linear dilaton still has some flavor of decoupling as the kind of corresponds to the string.
Yes.
Decouple the flow strength.
Exactly, yeah.
G strength.
Right.
Even though the geometry is sort of near horizon geometry, but the dilaton goes to. Decoupling goes to 0, you still decouple.
Yes.
Why do they call this TT bar then? Why would you call this TT bar?
Well, I guess there was a paper by Costasso and others who noted that if you look at the world sheet of a string in this background, it looks like a TT bar deformation on the.
Oh, on the string world sheet. Oh, I see. Okay. Oh, so this is a distinction between TT bar and the string roll sheet versus TT bar in the target space.
Yes.
Oh, okay.
We call it single trace.
I mean, I think she had a paper. I don't know if this was anyone interested was interested in that. We looked at like the non-singlet sector of a 2-matrix model of quantum mechanics.
Is this the thermal bootstrap one?
Yes,
Yeah.
one with the wider clouds.
Yeah, they look very nice. They could do so much with relatively small, well, apparently small number of operators. Well, I guess what was small is the total length of the operators. Large.
The graphs look very nice.
Yeah.
Or look very impressive. Yeah.
Yes. And they did two matrix model. So I guess, yeah, for one matrix model, I guess it's not surprising. You could do that for two matrix models. Well, for one matrix model, it's still nice. Not obviously.
Yeah, no,
More matrices.
no addresses exactly.
Or we can find, or we could find maybe a model with a smaller number of matrices that is equal to gravity. That would also be nice.
Right, there are many things to do, kind of. Yeah.
Also ask if they can with various parameters can define a criteria and tell us whether the model is likely to have gravity or with something they can test. I mean, of course.
What do these people actually do?
They consider the, I think, thermal expectation values of operators, and they bootstrap in matrix quantum mechanics.
Okay. With two matrices.
With yeah, first they did with one matrix, the non-singlet sector. I mean, just without imposing the transaction. H model. That they consider that was most of the paper, and that they consider the two matrix models. Give us a talk on entanglement and conjecture and complexity.
Okay, yeah, thanks. So, yeah, thanks for the chance to speak, and thanks also for the opportunity to visit. It's been really nice, and actually it's been super productive. The environment here has somehow given me enough mental space to work some things out and make some progress. Yeah, on this project. Okay, so what I'm going to be speaking about is entanglement implications of what's called the Python's lunch conjecture. And this is ongoing work, so stories may be still subject to some changes, but it's ongoing work with Chris Swedell, Sabrina Pastersky, and Michelle Zhu. Okay, so yeah, broadly, this work is dealing with this sort of interface that I think has been discussed a lot lately between gravity and complexity. And there's been lots of discussion in this area recently. So there's things like the complexity equals volume or action proposal from quite a while ago, and discussions around the complexity of the map from the bulk to the boundary in ADS-CFT. Recent discussions around maybe a role for complexity in cosmic censorship and of pseudo-entanglement and all these sort of things. One piece of this story that we're going to be interested in today, and that I think is nice, and that it's quite precise, is this Python's lunch conjecture. So yeah, maybe the first thing I'll do is just recall what this is and some of the details about it. So let's think about the boundary of some EDS spacetime and some subregion R of the boundary. So we know that the portion of the bulk that you can recover if you're given the degrees of freedom in R, the density matrix on R, is specified by the Ryō-Taganaki surface. So this is the minimal area surface homologous to R. We can also ask a different question, which is what portion of the bulk can you recover if you are computationally limited? So what portion is easy to recover in a complexity theory sense? And the Python's lunch proposal gives some proposal for an answer to that question. And they say what you should look at is another minimal area surface. And in particular, locally minimal surface that is outermost, so sort of closest to the boundary. They call that the appetizer. And it's this region over here between R and the appetizer that's supposed to be easy to reconstruct. And then this portion between the appetizer and the RT surface that's supposed to be hard to reconstruct. Okay, so beyond that, the proposal also specifies for
You
you.
have like a concrete setup where this sort of different.
Sorry.
You have a concrete
Oh,
setup
sure.
where this sort of different.
Yeah, good. Okay, so I'm drawing this picture. I have in my mind the ADS3 defect geometry. So I just have conical defects sitting at the center of the space-time. There'll be multiple geodesics that wind around this, and in particular, when I make R larger than a half, the globally minimal thing is here, and then there'll be some locally minimal geodesic that goes around the other side. So that's, yeah, an example.
Is that for some reason a better example than the black hole?
It's a little bit easier for drawing pictures, but yeah, the black hole is maybe the physically most interesting example. Any other questions just about the? Yeah.
Definition of gamma appetizer again.
Oh, it's so let's just talk about a like time symmetric slice of the space-time for simplicity, so I don't have to deal with sort of extremal surfaces, and I can say minimal. This is the outermost locally minimal surface. So I can deform this in some way, and every way that I deform it, it's going to increase the area. But its area may be larger than this other minimum over here.
How exactly do you define?
Oh, well, okay, in this number of dimensions, it's just a geodesic. So it would be a space like geodesic, that's the outermost one.
Outermost means closest to the boundary.
Yeah.
Labeled the boundary R.
Oh, sorry, maybe that's the confusion, yeah, yeah. Thanks. Okay. Good, so yeah, the proposal also specifies for you how hard it's supposed to be to reconstruct this region in here. So maybe I should say this region in here is what we call the lunch. Okay. And to specify how hard, we introduce yet another extremal surface in this.
Actually, is it possible to have like two different appetizers that I'll say like intersect in some way, so it's ambiguous which one's closest to R?
Yeah, I don't think so.
They proved it wasn't one of the papers. I thought you were in.
No, I wasn't. I haven't written about this
Somebody
before,
proved
but
it wasn't possible.
okay, thank you.
The rough idea is that if two of them intersect, you could
Smooth.
cut and paste, pick half of one and half of the other and then smooth it.
You'd have a corner, and then the corner is never minimal, and then, yeah, thanks. Yeah, okay, so how hard to specify that, they discuss another minimum or extremal surface, which is you should think of as a local maximum that appears between these two minima. In this defect geometry, this maximum surface looks like this, so it's two radial lines that connect to the defect. And this surface, it should be maximal in the sense that there's one direction in like the space of deformations of these curves that is a maximal direction, and then all the other ones will be minima. So in this case, you should think of that as the deformation you can make that lowers the area here is basically smoothing out the corner at the defect. Okay, so then
Ninthly, it should lower the area in either direction because you're going over a hill.
yeah,
When you draw the picture, it looks obvious that you lower the area if you move it to the right, but it's less obvious about moving to the left.
yeah, it actually smooths it out in both ways,
Okay.
but it's less obvious. Yeah.
I just want to, this is a very stupid question.
Yes.
Is, you were saying before that gamma RT was the global minima?
Yeah,
That means if like gamma RT, are you saying with entanglement or like the quantum, it's the global quantum minimal? You're saying that gamma app is the global, is the actual quantum extremal surface, right?
And no, so
I think he's not considering a situation where the quantum corrections are important.
Oh, okay.
yeah, right now, though, you could replace what I'm saying with the generalized entropy. And then you're talking about minima of the generalized entropy and so on.
Okay.
But yeah, this is the global minimum of, in the full definition, the generalized entropy.
Okay, I see. Sorry.
Yeah, no, that's good. Okay, sorry, so there's one more name here, so this maximal surface in between is the bulge surface. Okay. And then the proposal says that the complexity to recover from the lunch should be like 2 to the 1/2, a difference in areas between two of these surfaces, 4G Newton, where in particular, the difference in areas that I'm interested in is the area of bulge minus the area of the appetizer. And then there can be factors here that are polynomial in 1 over G Newton, but those aren't going to be too important for us. We're mostly interested in this exponent. Yeah.
You mean by recover from the node?
Let's say that I
Recovering something between.
yeah, think of some state in here, and I want some operations that will produce for me that state given this density matrix.
And that's if you're after the bulge, or is that anywhere between the appetizer and the RT surface?
Anywhere between the appetizer and the RT surface. So yeah, it doesn't matter whether you're in here or in here.
Okay.
It involves a factor of 2 or an exponential of it.
This is 2 to the 1/2 delta APL over 4G.
Okay.
Maybe my writing is funny.
No, that's fine. I thought it involved the areas, so I was remembering correctly. That it involved an exponential of the areas.
Yes,
Like
that's
a ratio of entropies, but something that looked like a ratio of entropies, but that's not.
No, it's an area in an exponent. So it's 2 to the area difference.
I maybe this may not be, but I'm just wondering whether it's an e to the areas, but it doesn't matter.
Oh,
I'm worried about the 2's versus the versus an e.
oh,
It really should be E because our entropies are in maths rather than if we're using the.
Well,
RT formula.
I think what I'm going to say in the end is going to be insensitive to that.
Okay.
But in the paper, they write this, so I'll just write this.
Okay.
Yeah.
This comes from assuming that the Grover search algorithm is optimal.
That's right.
Yeah, okay.
Yeah.
That they derived this by assuming a Grover search. They say it doesn't matter. Sorry, I was.
It's surprising that the factor of 2 would the 2 would appear because the dimensions of Hilbert space and so on are
Yeah.
yeah.
I mean,
networks and so on are exponentials with an e.
I'm going to end up taking a logarithm, so I think it won't matter for me in the end, but yeah. Okay, yeah, so okay, so this is the proposal. It's quite precise. It claims a particular exponent here, for instance.
Well, if you're claiming a particular exponent, you better know whether it's 2 or 3.
They write down 2 to the 1/2.
Yeah.
But okay.
And logic should have given E.
Okay, so the goal in the work that we're doing here with my co-authors is to try and give some sort of way to verify this proposal. So we want to find some consequence of this proposal that you can actually do some computation and check whether it's holding or not. And naively, this seems really challenging because this quantity on the left, this complexity, is well, it's hard to define precisely what you mean by this in a CFT, and then even if you define it, typically a complexity, even in maybe some simple computer science model, is it's not really something that you can compute. So, okay, how do you check this? But yeah, I claim that we'll get to some calculation that's concrete, where that's an output of this conjecture. Okay. So yeah, I won't review the motivation for this conjecture. But I just want to tell you one more thing about it.
One quick question, can you remind me, I guess the surface PP, could it ever happen that the surface PP is strictly within a causal wedge?
Oh, sorry. No, they prove that it's actually outside the causal wedge. Yeah, this is a paper with Netta and Jeff and maybe Arvin and a few people.
Yeah, I think the idea is that the Ricciarduri equation implies that the area would decrease, right? So if it is extremal at one point and then second derivative is negative, decreases, so it can never reach the boundary. I mean, the light rays coming from there can never reach the boundary.
Yeah, okay.
Yeah, okay, good. Yeah, so that's some sort of consistency. Yeah. Okay. Good. So yeah, so I just need to tell you one more thing about this proposal, which is a distinction that they make in the original paper between sort of two types of lunches. So one is, well, let's say fixed size lunch in a particular sense. So this example that I just drew would be one example of that. And in particular, what I mean is that it's fixed size in ADS units as G Newton goes to 0. And by size, I mean the volume. So the volume here would be some power LADS. So I mean, I think of this as fixed as G Newton goes to 0. If I measured it in Planck units, that would be a confusing statement, but. Okay, and then distinguish this from large or growing lunches, which occur in these sort of black hole contexts. So you might be familiar with a picture like this. So here I'm drawing a cartoon of an evaporating black hole, and we have some bath in which I've collected the radiation. There's this entanglement in between the radiation and the interior modes. And here, after the page time, the RT surface is over here near the horizon. And then the appetizer surface is a quantum extremal surface that's cutting the radiation between the interior and the exterior. And here, you should think of as G Newton gets small, basically that pushes the page time later, and this interior has grown more, and so the volume here has some extra dependence on, and then in particular is big as G Newton goes to 0. Okay.
So the RT surface is there. Oh,
Yeah, I thought gamma, you have their gamma appetizer cutting entanglement. I thought gamma appetizer was like a semi-classical art, like it was a semi-classical region in space-time. Like I have my two competing surfaces, and then I have this I can just compute what the maximal area is, like do the opposite of what you're usually doing with the RT surface. But then here this is a different picture than that. It seems like
yeah, I'm just saying, like in these recent, well, not quite that recent, but in these computations of the page curve from the Ryutakanaki formula, there's like two candidate quantum extremal surfaces, and after the page time, they exchange dominance.
yeah.
And in particular, after the page time, you can reconstruct, a portion of the interior of the hole, and your RT surface is close to the horizon of the black hole. this is in your entanglement wedge.
You're drawing the appetizer of the radiation.
Yeah, that's right.
Okay, sorry.
So I'm looking at thinking about the entanglement wedge of the radiation, and then there's this, this other quantum extremal surface, which is like excluding the interior that you can, picks up some bulk entropy term from the entanglement between the interior and the radiation.
Yeah, okay, sorry, I think that was mixed up with what you were calling. Okay, sorry.
Yeah,
So I'm still confused. Geometrically, gamma appetizer is outside of the black hole or inside?
it is, well, it's a quantum extremal surface, so maybe that doesn't totally make sense, but the portion of the space-time that the equation is reconstructing is not including the interior of the hole at this point, so you should think of it as outside.
It doesn't have an area piece. It only
It
has
doesn't have an area.
It just only has a quantum entropy piece.
But if it doesn't have an area, how are you applying this?
Sorry, I kind of skipped. So the right way to think of this in the most general setting would be to have replace everything with a generalized entropy. And so there's some bulk entropy terms appearing. And in some cases, so this would be like S gen of the bulge, and then S gen of the appetizer. Okay, and then you can have these entropy terms appearing, and that's corresponding to this kind of cut here.
What goes for G?
The size of the interior of the hole. But okay, so yeah, the reason I wanted to raise this distinction, this is a distinction they make in the original paper from Brown and Susskind and Jeff and Hran, is that this fact that the volume of the lunch is growing with G Newton is actually important for their argument. Okay, and they say, we can still think about lunches in this setting, but you should be circumspect of conjecturing this. In that case, because a piece of their argument, this argument that this particular algorithm, the Grover search algorithm, is optimal, is relying on the lunch being large in some sense.
Growth with G Newton means that G Newton goes to 0.
Yes, sorry. That grows in the semi-classical. Okay. Okay, so that's everything I need to tell you about the lunch proposal. Now I want to start explaining how we're going to put this to some kind of a test. And the key sort of tool from quantum information theory that I'm going to use to do that is a notion from cryptography called conditional disclosure secrets. Yeah.
Does it go with one of Newton when you keep the mass of the black hole constant, or?
Yes, each time will occur later. Yeah, it's like making the area term larger, but not really changing this term. And so it's making you wait later until you can. Okay, so conditional disclosure of secrets. This is somehow going to bridge for us, I claim, these two worlds of complexity and entanglement. Okay. CDS is somehow going to connect these. And what that's going to let me do is turn some statement about complexity into a statement about entanglement, which is something that I actually know how to compute things in ADS-COT. Okay, so the basic setting here, some kind of quantum information processing setting, and it involves three parties. There's Alice, there's Bob, and it's the referee. Okay. Alice and Bob don't talk to each other. They can each send a message to the referee though. Alice gets an input, well, two inputs. First is a string X of n bits. And the second is, or sorry, and she gets another input, which is a string S of some other length. So this is n bits, this is, I'll call it n sub s bits. Bob gets an input, which is a string Y of n bits. Okay. What they want to do is send messages to the referee such that the referee can recover this string, which we'll call the secret, if and only if some sort of relation on the inputs X and Y is met. Okay, so we'll think of there's some Boolean function that takes values in 0, 1 on X and Y. And if this thing is 1, the referee should get the secret. And if it's 0, the referee should not be able to learn the secret.
And as you've defined it, this is a classical problem because you're not considering superposition of sequences. You're just saying, I have some sequence of numbers and some sequence of numbers. I'm not considering linear combinations.
I am going to allow Alice and Bob to share quantum state, quantum operations, and send quantum messages. The referee could also do some quantum operations. But yeah, the inputs and outputs to the problem are just classical, but they might use quantum resources along the way to try and do it. Yeah.
When we say getting the secret, does that just mean with better than 1/2 probability? Or
Yeah, we're going to be more precise about that in a second.
Okay.
Yeah.
F is going to be a function that's usually not 1. So
Yeah,
that's-
F is going to be some, the interesting case is when F is some non-trivial function. Yeah. That depends, on X and Y. Okay, so yeah, well, okay, so this is studied pretty well in classical cryptography, or the classical version of this, where they just share like shared random bits. Is studied a lot in cryptography. My group recently started studying this in a quantum context where you allow quantum resources. It's an interesting subject. It has lots of applications in cryptography. One thing that's kind of interesting about it is that naively it seems sort of impossible. So, you can imagine you're Alice, you're sitting there, you hold the secret, right? You hold X. You could choose to send the secret to the referee or to not send it, but you don't know why. And so in general, you don't know the value of the function f of x, y. And so what do? Do you send it or do you not send it?
What's
yeah.
the purpose of this game?
Uh,
It's like, I just want to hide his secret, or how the referees knows.
Yeah, this you should think of as, in cryptography, it's viewed as some primitive, so it's not in itself something that you might want to do. It's something that you would use as a building block to do other useful things. For us, the purpose is, well, I'm going to get to the point of why this is for us in a second.
Oh, okay.
Yeah.
So intuitively though, Alice wants to send the message if only if Bob has some information about X.
If and only if X and Y are related in an appropriate way. So an example, well, I'll give you an example in a second, but you could think, suppose that F was the equality function, like you want to reveal the secret if X is Y and not otherwise, for instance. Yeah, okay, so it seems hard, but it actually is possible. You can do this for any choice of function, f of x, y. Somehow you have to encode the secret in such a way that the referee, is able to decode it if and only if x and y are related in the right way. Okay, yeah, so let me give you an example. So yeah, like I was suggesting, let's, as a simple case, take f to be the equality function. So it's going to be 1 if x equals y and 0 otherwise. And also for simplicity, let's take everything to be a single bit. So x is just 1 bit, y is 1 bit, s is 1 bit. Then I want to explain how you can actually do this. So here's the setting. X, Y. The message that, let's say Alice is going to send is going to be the sum S and, oh, sorry, let me step back. So we're going to need to have Alice and Bob share some sort of correlation. In this example, we're just going to have them share classical random bits, which I'll draw like this. So to be clear what I mean there, we should think of like we flip a coin, we get a random outcome, take that random outcome and we give it to Alice and Bob. The first outcome we'll call it R0. Flip the coin again, call that R1. So they both hold these.
The share means they both know.
They both know the outcome of that coin.
Oh, okay.
Okay, so there's R0, R1. And then what Alice is going to send is the sum of S with the random bit labeled by X. Okay, so X is either 0 or 1. If X is 0, you should add S and R0. If X is 1, you should add S and R1. Okay.
They only share 2 random bits in this example.
They only need 2 random bits in this example, yeah. My funny plus here is the XOR, so that just means that I'm taking the sum mod 2. So 1 plus 1 is 0 here.
You're also taking X and S to have the same number of bits, possibly.
Yes, that's right. Everything's a single bit.
No. Well, only a single bit, okay.
Yeah, for simplicity. Okay, then MB is going to be R sub Y. So Bob reveals one of the 2 random bits depending on his value of Y. Okay, so then why does this work, right? Well, let's say that F is 1. Then
So X and Y are assembled, they choose Y, the value of X and Y.
you should think of X and Y as given to them maybe by some third party or set randomly. Like Alice and Bob don't get to choose X and Y.
Oh, okay.
And in particular,
They're given, okay.
yeah, like Alice knows X, but she doesn't know Y, which is important.
Oh, they don't know X and Y value each tree.
They only know the value. Okay, so let's suppose that F is 1, right? Then we're supposed to be able to recover the secret. If F is 1, X is Y. So Rx is the same as Ry. So if I'm the referee and all I see is the messages, I can compute MA plus MB and get the secret, right? The Rx and Ry are going to cancel out and I'll just get S. On the other hand, if F is 0, then this bit of randomness and this bit of randomness are different. So this just looks like a totally random bit, and this ends up looking like a uncorrelated, also completely random bit. All the referee is getting is 2 bits of randomness, 2 bits of junk. She doesn't see anything about the secret.
Does the referee also get X and Y so that
Yes, you get X and Y.
Oh, okay. So the referee know X and Y, but Alice only know X and the Bob only knows Y.
Yeah.
Oh, okay.
Yeah.
So the referee doesn't know if he got the secret or not.
Well, the referee knows X and Y, so they know F of X, Y.
Oh.
So they know, oh, X equals Y, I should do this computation and that's going to correctly give me the secret. Yeah.
Sorry, I just want to summarize the logic. So if X is not equal to Y,
Yeah.
the referee does not have access to S.
Yes.
That's the point of this exercise.
Yes.
And if X is equal to Y, the referee does have access
Yes.
to S. So the goal referee is trying to access S using whatever it can, while the goal of Alice and Bob is for referee to only access S if X and Y is equal to.
Correct.
Sorry.
Correct. Okay, so I'm definitely going to run out of time, so I'm going to try and say. Okay, yeah, I want to make one more point, which comes back to somebody's question, which is, well, okay, also, so here in this example, when F is 0, the referee just holds stuff that's totally uncorrelated with the secret. In particular, there's no computation they could possibly do to recover the secret. We call that in cryptography information theoretic security, okay? We can relax that to a notion of computational security. So we just require that a referee of some bounded computational power is not able to compute the secret from the message. Okay. So we're gonna need a slightly more precise definition of what I mean by that. What do I mean by computational security in this case? We're gonna require that when f of x, y is 0, the ref, if they use some amount of complexity t, has the following. So the probability that they can correctly guess s should be bounded, let's say, by 1/2 to the ns. So this is your probability of getting, if you just completely randomly guessed, right? 2 to the ns is the number of possible values of the secret. And then we're gonna allow some relaxation of that depends on t and some other parameter I'll call lambda. So this function delta t lambda should grow with t in some way, but for small t should be small, right? And in particular, I'm going to require that. Okay, so there's also this other parameter that I'm calling lambda. Cryptographically, you'd call it a security parameter. So it's some sort of knob you can turn to make this thing safer. And in particular, what I mean by that is this should be true. So as I take lambda big, this should go to 0 at fixed t. So you should think of this as like, you know, typically in a computational problem, there's some like size of the problem that controls how hard it is. Lambda is sort of that size of the problem. And when you're making it big, the problem's becoming very hard. And your probability of getting S correctly is just approaching the random guessing value. Okay.
Are we scaling lambda independent of how much quantum information Alice and Bob share?
Well, we're interested in like how much correlation do they need to achieve a given level of security?
I see. Okay.
So that actually brings me to my next point, which is a lower bound on how much correlation they need. Is the following. So prove the thing, which is that if you do this computationally secure CDS, then the correlation in your system needs to be lower bounded like this. So there's a minus log 1/2 to the ns over 2 plus the parameter delta. So ns was the size of the secret.
Is it related to psi AB?
Psi AB is this this system that Alice and Bob share, and then this mutual information is measuring how much correlation is in that system.
So does this depend on what message is Alice and Bob send to the referee? So that is a very specific example, but does this theory rely on how the format of the message is?
Well, we're assuming that the format of the message.
Yeah.
This is saying that like for any protocol, any method of accomplishing this that you could try and do, you need to have correlation to start out with that's lower bounded in some way. So yeah.
I see. Okay. Do you have give us an intuition why the entanglement, like mutual information side, play some role here?
Yeah, I mean, well, okay, I could say more, but maybe for brevity, I'll refer to this example, and hopefully this gives you some sense of how the fact that you had these correlated bits was important for accomplishing this goal. Okay.
So for example, if you had only one, it wouldn't have worked.
That thing wouldn't have worked, yeah. This is actually show that no protocol, like this is a protocol that uses this correlation. you can show that there does not exist any protocol that without the correlation would have succeeded in doing this.
Oh, I see.
So. This case, IAB is 2 or,
Yes,
and when you say 0, you mean that you assume that the probability is higher than that? Or when this is correct? Correct when you succeeded to?
yeah. So,
Yeah, so when there's a point.
yeah, I mean, you could plug in the numbers here and these things should be consistent.
Sorry,
Like you could plug in the size of the secret and this worked perfectly. So that gives you some, I don't know, I think this lower bound will give you like 1 in that case, whereas actually this thing I needed 2, but it wasn't completely tight.
Did you actually use sort of complexity theory to prove this or?
No.
Like T doesn't really enter the formula, right?
No, that's right. So this also applies, I think I misspoke when I said it, but this also applies to the information theoretic case. The complexity theory is going to come in when I specify what delta looks like.
Yeah, okay.
And the complexity, this T parameter is going to enter via delta. Okay. So yeah, okay. All right, let me try and get back to the holography out of the computer science. Okay, so the idea here is that we're going to.
The statement is that that's needed to succeed with probability bigger than 1/2 to the ns plus delta. I guess.
Yes, that's right. Yeah.
But delta is just a number, you know.
Delta is a number. Okay, so how this is going to come into holography and relate to the Python's lunch is that what we're going to do is somehow use the bulk geometry, use the ADS geometry to accomplish this sort of CDS task. Okay, and when we do that, the way that this thing is going to become secure, that it's going to be hard in one case and easy in the other case, is we're going to put the secret into the Python's lunch or keep it out of the Python's lunch. Okay. Okay, and then what's going to happen is that Python's lunch geometry is then going to get related to some measure of correlation via this theorem. Okay. Okay, so let me try and explain that. So here's my ADS3 sort of cylinder. So we have, well, let me first of all say we're going to pick some boundary region that I'll call R. And you should think of that as the portion of the CFT that the referee gets to look at in my setup. Okay. And then I'm going to be interested in where the appetizer surface sits. So I'll draw that, and I won't draw the RT surface. And then we're going to think of 2 points at some earlier time, C1 and C2, which are where the inputs X and S and then Y are going to get introduced into the bulk. Okay. Okay, and then we're going to think about bringing those inputs together in the interior, meeting somewhere. At that point, computing f of xy, and then sending the secret conditioned on the value of that outcome function, either into the easy to reconstruct portion or keep it out of the easy to reconstruct portion. Okay, so let me give this easy to reconstruct portion a name. That's going to be ER easy, it's the easy wedge. And the aspect of the spacetime that lets me do this, or the thing I have to assume about the spacetime to be able to do this, is that the following intersection of futures, or the following spacetime region is not empty. So I'm looking at the causal future of the point C1 intersected with the causal future of the point C2, intersected with the past of easy wedge, the past of the complement of the easy wedge. So okay, that's a definition. And then the observation is just that if this thing is not empty, then this is letting you sort of accomplish this CDS thing. Because you're conditioned on the value of F, making the secret easy for the referee to reconstruct or keep making sure it's hard for them to reconstruct.
Who is it who's computing f of xy? The referee?
So think of that as happening in the bulk. So I would think of it as Alice and Bob jump into the bulk and they bring X and S in and they compute f of xy and then they choose to send S here or not.
Well, and that's because Alice and Bob were working together. I thought they were kept apart.
Right, but this is the bulk picture. In the boundary picture, or yeah, an important thing is that in the boundary picture, the structure of what's happening is going to look like this. And while in the bulk picture, somehow the fact that EDS-CFT makes this geometrical picture out of entanglement means that in the bulk, it looks like they're meeting.
Okay.
Yeah. Okay, so let me try and draw this in the boundary. Here's some region R. Here's the space-like complement of R. And C1 and C2 are at some earlier time. I'm going to be interested in some regions defined like this. They're defined by the future. So B1 is the future of C1 intersected with the past of R in R complement. Similarly for B2. And then the point is that here in the boundary picture, the structure looks like here. Looks just like this, where the fact that Alice can send a message to the referee, that's corresponding to the fact that C1 can send things to R, C2 can send things to R, and then this correlation between Alice and Bob, I'm identifying as the correlation between V1 and V2. Okay. So what we get then is if this region J is not empty, then by looking at the bulk picture, we're seeing that you can do this CDS thing, you can sort of accomplish the outcome of the CDS. And then in the boundary picture, we're seeing that it happens really in this form of, with this structure that's constrained by this theorem. And so we're getting some lower bound on the mutual information like we have in this theorem.
I do know.
So by reasoning in the bulk, we know like if this space-time region is not empty, then we can do this process that I'm describing here of just meet and compute F and then send the secret in or keep it out.
Or you could say you send machines in that are programmed to do it.
Yes, it's probably better.
Say Alice and Bob jump in.
Or Alice is a computer or something, but yeah, that's right.
So for it's non-trivial to say that you have a machine. They meet so they can.
Yes.
Okay.
Yeah, as long as the space-time region is open, then I can do this.
I think I'm slightly confused by something in the boundary picture.
Yeah.
In order to get up to the region R, which is where the referee is living, right? Doesn't the boundary Hamiltonian look like it's directly coupling the degrees of freedom in C1 and C2 because like Hamiltonian X kind of also them? So doesn't that allow something more general than on the right, where the picture on the right, it looks kind of like there's a separate evolution from C1 up to the top and C2 up to the top.
I think, yeah, I think maybe
time slice, yeah.
Yeah, exactly. You should think of a time slice like this. And this is, or some portion of this is the message that gets sent here.
Okay.
And this is the message that gets sent here.
This is just a statement that the Hamiltonian evolution.
Right. This time slice, okay, but then the region R is lower than you drew it, right? I mean, it should be the causal diamond of just the intersection of that segment with what it says R, right? Why does the R looks too big, right? That's what I'm confused. Picture.
Yeah, but well, R looks too, like, you want R to be,
Like, in other words, I would have thought you didn't want R to contain points which were in the, well,
yeah, you want R like this or something.
wouldn't you want R to be maybe a union of two regions or something? One in the causal future of C1 and the other in the causal future of C2, but didn't have any points that are in the union of the causal futures of C1 and C2? Because then they could have been, then there would be a combined Hamiltonian, right? Which looks like a general protocol. Maybe I'm missing this now.
I think, okay, I'm not sure well, yeah, I'm not sure I totally understand. I mean, maybe one way to think about this is just like, we pick some R, we pick some C1, C2, where the inputs get put. And then there's sort of only so many light cones you can, and you're trying to identify what I should think of as this thing. And there's basically only one combination of light cones that makes any sense, which is this one. Yeah, maybe.
I'm just worried about whether the propagation between C1 and C2 up to the referee allows an interaction of Hamiltonian, but that seems like it's not supposed to be allowed.
Well, I mean, V1 and V2 are separated, so as long as my Hamiltonian is local, I don't think I'm coupling the stuff in here.
Oh, here, it's in V1 and V2 that you're gonna, that's where the referee lives.
Oh, the referee lives here. This system is identified as this. So, you know, this thing is not interacting with this thing, which is like Alice is not talking to Bob.
Yes, okay, I understand. And then if the referee lives up there, doesn't.
Well, the referee's allowed to involve Alice and Bob.
Oh, the referee can involve Alice and Bob together.
Oh, okay, sorry, maybe.
Oh, I understand.
Maybe I wasn't understanding.
Okay, no,
Like, yeah, that's right. So Alice, the ref combines the two messages and hence.
I see the logic.
Does this protocol require some entanglement? So in the picture, the boundary picture, it looks like there is some entanglement between R and Alice and Bob, between the referee and Alice and Bob.
That's,
yeah.
Yeah, okay, so that is actually, okay, so you've caught a subtlety. There's really, if I want to model this correctly, some like 3-part state with entanglement between here and here and here, yeah. Okay, so there's a weakness in what I've done so far in that I actually don't know how to make this bound work. In that case, where you have this 3-party state, I only know how to make it work in the 2-part case. The intuition is that things are not going to change between those. But, okay, part of that intuition is informed by earlier work that I've done where I drew similar pictures and the same assumption appeared and was okay in that context, but okay, these are some details.
Maybe, yeah, okay, maybe you can just restrict that the referee does not use that amount of entanglement.
Yeah, the intuition is basically that like this 3rd part is kind of universal, like it isn't like Alice and Bob kind of can't make use of it because they don't act on it. It's the same regardless of X and Y, and yeah, when you look at these things, it seems to not be helpful for them, and you always need this correlation. But yeah, that's a part of this argument that is not rigorous.
Has that gap been filled in the other cases, or are you just saying that the results appear to make sense?
So in the other cases, this connected wedge theorem stuff with Jeff and John, that gap appears in the quantum information argument, but then we prove the outcome of the quantum information argument in the gravity context. And so that gives us some confidence that, you know, this sort of model was actually a good one. And then there are some cases in that context where you can actually close it and you can remove sort of that 3rd system. And I haven't understood how to do that here yet. Yeah. But okay, I should probably try and finish in 5 minutes or something. Okay. Okay, so yeah, we get this lower bound. This isn't very meaningful yet because there's these funny parameters and S and delta. And, okay, in the interest of time, I'm going to skip some of the argument. But basically, the point here is that this delta depends in some way on T. Well, okay, actually, I should say a little bit more. So there's a claim here that that we should take delta to be like this. So why do I claim that? So this is, if you assume this Grover algorithm is optimal in a particular sense for recovering from the lunch, this is the delta that you would get, okay? And, you know, there's an important point here, which is that I have to assume that, at the moment at least, I have to assume that algorithm is optimal. In a larger regime, then you have to assume to get the statement of the lunch conjecture. So the lunch conjecture I would frame as saying, if you want to recover with fidelity close to 1, or in this case probability close to 1, then the Grover algorithm is optimal. This is following if you say, even when I try and recover with some, you know, small fidelity that's just better than random, that the same algorithm is also optimal. Right. So yeah, this is important because it means that the consequences that we're getting are not quite, at least yet, from sort of the minimal version of the Python's lunch conjecture. It's from instead, yeah, this thing that I just said. Right.
I'm a little bit confused. So if the delta is larger, does this mean that it gets correctly have a higher probability?
That's right, yeah.
Okay, but
Yeah.
I'm
So-
just confused that then in that case, I want delta larger, I want the T to be large, means I
Yeah.
should send into the
So T remember is the
region.
T is the complexity that I'm allowing the referee to use. So this is saying that if I take T of this order,
I
I
see.
recover with probability 1.
Oh, I see.
Which is, so when T is big, that's the regime that the lunch conjecture is talking about. I'm sort of extending that into an extended regime.
Oh, I see.
Okay, so yeah, so you have to make this claim. And then you can think about this lower bound and the way that you can choose NS. You can basically get this term to be small compared to delta and get the lower bound to have this come out. So what you can end up with at the end of the day there, if you take this claim, is that you get speech confirmation. You want to lower bound it by something like this. A little bit annoyingly, because you have to look at the small G Newton limit and you're doing some sort of asymptotic analysis, you end up losing the constants. And so there's some arbitrary constant alpha naught here that appears. Right? And so this is why I wasn't worried about 2's versus e's, because I can't see them anyways in this check.
Wait, sorry. What?
Well, you aren't really expecting to prove that the Grover search gives the right constant in any event, are you?
Well, certainly not using this technique.
Yeah. So you must have an unknown constant.
Yeah. So this thing pops out of the analysis. But this is still some kind of precise, well, okay, so this arbitrary constant means that if I look at any one geometry and I compute, well, okay, so I should say, what's nice about this is that I can compute both sides of this, right? Everything here is areas of extremal surfaces. Now, if I look at any one geometry, this is not a meaningful check because I don't know this value, right? I compute this number, but there's an arbitrary number in between, so I don't know what's happening. But what you can do is look at families of geometries and make sure that, so you should never have within some family, you know, some way of moving through the parameters of that family such that this is going to 0, delta APL is staying positive and finite. Okay, so that's the kind of check that you can do. Well, you should also see that if you, so that's the check we're gonna be interested in right now.
By looking at examples, we get a bound on this alpha zero.
Yeah, in examples, you get bounds on alpha zero.
Does it look like an interesting number?
Well, yeah, so actually the surprise here, which, yeah, so I might have described this work to people earlier and not had this because I thought about this over the weekend, but there actually seems to be a counterexample to this statement. Okay, so either one of these assumptions that I've made along the way, like the start thing, is incorrect, or the lunch conjecture is not applying in this example. The example involves taking two intervals, and I'll try and finish up. So R here is going to be the union of R1 and R2. And I'll apologize to Juan because he asked me when I got here if you could look at this example, and I said, no, you can't look at this, it doesn't make sense. And then as soon as I said that, I said, why did I say that? And it was some belief from early in the project when I didn't really understand things. And so rethinking it, realized, you can think about this, it's totally fine. So yeah, we're going to look at this example that we can say do this just in pure ADS, and there's a lunch here. In particular, if these are big enough, then the RT surface is these connected surfaces like this, and then the appetizer is these two separated ones. Okay, so that's going to be our region R, and then the boundary. I don't want to use too much word here. So the boundary then one and R2 together make up R, and then there's the complement R prime, right? Prime. This could be R1 or 2. Okay, and then you can choose C1 here and here. So they should sort of be before this line so that V1 and V2 are these nice domains of dependence. There's some parameter here, which I'll call T naught, which is how far down I took C1 and C2. And yeah, what you can see is that there's some like critical T naught, okay, above which you have J is not empty. So if I pull this down far enough, then I can do this kind of process in the bulk. And what happens as T goes to T, or as T naught goes to T critical, is that the mutual information goes to 0. Even while, yeah, so the mutual information goes to 0. When it hits 0, this is turning off, but strictly above this value, I have this scattering and this is getting arbitrarily small. And then the whole time here, I'm not changing R. So this is some fixed number. Okay. So that is in contradiction with this statement.
Is T critical the point where the point C, the future of the point C wouldn't overlap with R2 at all?
No, it's like here somewhere, like it's just some like you're not going up to the slice of R1, it's at some, or that wasn't what you're asking, sorry.
Yeah, I'm just a little confused by the angles of the lines in the picture. So the point, the region V1, if I propagate along the light cone to the left,
yeah,
it hits R1 or whatever that's called, R2.
Oh,
R2 is supposed to be in the causal future of V1 or not? I couldn't tell.
It doesn't matter.
It doesn't matter.
have to check the example if T naught is related to like, you're saying, is it related to this? Like, I don't know, actually. I would have to look at the example in detail.
Because I guess if it's.
But so the important thing here is that V1, like, or VI, still the future, it's defined just like before. So I was defining it as, well, I guess I didn't write this down, but it's like this. And that's true in this example, and that's also the way it was defined here.
When you do this, probably this point that is in the hard to get region is approaching the boundary, right?
Sorry, which?
Sorry.
Oh, these, like, this.
Well, I was wondering whether in this setup,
Yeah.
That point, this point here.
Yeah.
Where this point is approaching the surface.
It is actually, yeah.
Yeah.
So the scattering is turning off.
Because
Getting very close.
one would think that this is a doubt I had about the Python's lens
Yes.
conjecture, which is a statement about whether you can reproduce something anywhere in the lab. Because it sounds intuitive that it might be easier to reconstruct something that is closer to the surface than something that is a little further.
Yes, and yeah, so the statement of the conjecture is that, you go past that surface, it's immediately this full complexity. This, like, a way out of what I'm showing here would be that as you get close to the surface, it is actually easy or easier. Yeah, so that is one possibility. Yeah, the other one that I want to.
Tensor network picture suggests that because you have this projection operators, right? You would have to undo a smaller number of projection operators.
Well, yeah, that's the thing. I actually got confused about this at one point, and Jeff had to set me straight. But so you can't actually, like, the reason they make this claim that it's full complexity once you go in is that if you try and, like, it's not an invertible map to try and undo part of the projections. The only thing that you can tell is invertible is, like, undoing all of them. Yeah, and so that's why it seems to be this full complexity.
Your statement there that once I pass it, I have to undo all projections. It doesn't matter if the state is being projected by fewer, you're just because it could be. Like, the statement is you could have any projection past that point. So you need to undo all of them, even if there are fewer projections actually acting on the state.
Well, no, it's like, so this map, like, it's not clear that there's a map which is invertible from, like, some small portion of the lunch out to the boundary. The thing is invertible is the map from, like, the full lunch out to the boundary. And so you end up in their algorithms, like, undoing that whole thing. And that has the full complexity. But okay, I'm really over time. Let's say one point that I think makes this maybe a little bit less surprising, less jarring at least, which is, so I mentioned at the beginning this distinction between lunches of a fixed size, growing lunches, and that their argument is, like, strongest in the case of lunches that are growing in the semi-classical limit. And they mentioned that you should be circumspect of the other case. This is in the other case. So the example that I'm finding is in a case where the lunch is of a fixed size. And so maybe that's another way out, is that the lunch conjecture is applying for growing lunches, but not fixed ones. And examples like a black hole where we have sort of physical reasons that we want this to be hard are occurring in this this case where we're more confident in the lunch conjecture that the lunch is growing. But okay, let me finish there.
I didn't fully understand the star claim. Is it equivalent to the thing you were trying to prove in the beginning? Or?
So I think you should interpret the Python's lunch conjecture as saying, if you want to recover with fidelity close to 1 from the lunch, then you need this complexity. This is saying that, well, basically that something similar is true, but also at small fidelity. So if you want to do a little bit better than randomly, then the same kind of algorithm is optimal. Yeah, so this is, you should think of this as a stronger claim.
Which you're finding is probably not entirely correct.
Yeah, so one way out of this is that claim is not correct. I actually suspect that that's not the case, or, you know, maybe I'm being a bit bold in doing that, but there is like a way one can hope to show the same lower bound in terms of this complexity without making that assumption. Like at the QI level, there's some technical route forward for showing such a thing. I haven't succeeded in proving that theorem yet, but I suspect that it's true. And so, yeah, that gives me some, well, that gives me some intuition that this actually isn't the issue, but you know, I shouldn't bank too hard on things I actually haven't proven, I guess. So.
I have a naive question about understanding the one just raised. So that probability is bounded by like a red Gaussian plus the delta.
Yeah.
But there are two choices for the message to be sent in the launch or in the appetizer, right? Will the probability be different for?
Oh yeah, that's right. So
yeah, I think you didn't differentiate these two cases.
Sorry, yeah. So we want it to be that when f is 1, you can recover with very high probability.
Yeah.
And the way I wrote things down, it's like I'm assuming that it's probability 1, and then you should actually take it to be probability sort of 1 minus epsilon and carry the epsilon around. Be careful, but yeah. So the task or the thing you're trying to do is when f is 1, make it easy to recover in the sense that you get it with high probability, even using low complexity. And then when f is 0, with some given complexity, make it, you know, small. Make the probability of recovering small. And that in the AS picture is corresponding to send it, you know, when f is 1, you send it into the easy region, and when f is 0, you send it out of the easy region.
Okay.
What does the size of our secret correspond to in our bulk boundary picture? It seems as though.
Yeah, so yeah, okay, I didn't discuss this. So the size of the secret, so okay, you're thinking that the way of thinking here is we're thinking about some sort of thought experiment where these processes are happening in the bulk, and then we're reasoning about what the boundary needs to reproduce that process. I get to pick my thought experiment. In particular, I get to pick how big of a secret I want to put in. You should pick it to be small enough that it's not forming the geometry you're talking about. But then I have to pick it large enough that this term is sort of subdominant compared to this one. And so there's some subtle way of doing that leads to this lower bound.
I see. I mean, theoretically, I could take any bulk or boundary I wanted with V1 and V2 and just pick a secret big enough such that it saturates this or that satisfies this boundary.
Yeah, you can. Well, you can't pick it too big because otherwise you're going to change the geometry that you study.
Makes sense. Okay.
But yeah, you're kind of free to choose it.
Okay, thank you.